right on time, which arguably for this class is always 5 minutes late. So let's do a week at a glance quick. So we got Monday, Tuesday, Wednesday, Thursday, Friday. So we're going to lecture on chapters 9. Oh, I'm sorry, we're skipping chapter 9. So lecture on chapter 10, lecture chapter 10, lecture probably chapter 10 and 9. So we're basically, no, because what we're going to do is, and then we've got Monday, Tuesday, Wednesday, Thursday, Friday that following week. One of these 2 days will be a test on chapters 9 and 10. Friday for sure will be a review for the final. And then I usually, depending upon, and it really just depends on where we get done with stuff, we'll also have like a review. Well, we'll probably have the test on Wednesday. And it really just depends on how kind of quickly we go through this. But I usually spend 2 days reviewing for the final. And then, of course, finals week is Monday, Tuesday, Wednesday the following week. And there's 2-part final. There should be chapters 1 through 4 or 5 and chapters 5 through 10. I don't know where I'll stick chapter 5. Chapter 5, yeah. Because like chapter 6 technically doesn't count. It's such a tiny little chapter that it really is part of chapter 5. And so I usually do it 1 through 4 and 5 through 10. And then obviously we're going to lecture on these days too. And on this day, may or may not have class. Sort of depends on the weather. So where we're at on chapter 10 is we had finished, so I won't actually review it, but what we had just got done talking about was the intermolecular forces responsible for holding molecules together. And what now we're going to look at is sort of how those intermolecular forces affect the properties of different things. So what we're going to look at now is the properties of liquids. And some of the properties we'll look at just qualitatively, and some of the properties we're going to actually look at quantitatively. So the first property we're going to look at is simply viscosity. And that's the resistance to flow. And probably the easiest way you can think about this is water, say, versus SERP. We know that water flows very easily, whereas SERP flows slowly. And if you think about it, this resistance to flow, or the idea of flow, is that it's proportional to the intermolecular forces. And when we say the intermolecular forces, we're really talking about their strength. So if I have low intermolecular forces, meaning weak attractive forces, then I generally have low viscosity. And then if I have strong intermolecular forces, meaning I have strong attractions between those molecules, then I generally have what I would call high viscosity. So this would be low, high. Now, we also have to factor in the shape of the molecules, which arguably means that it's not very easy to necessarily make predictions on the viscosity of things if you don't know the shapes of molecules. And really, for most molecules, we don't know it. So what we're going to say is that things that have low viscosity generally tend to be nonpolar and very small molecules. and that things with high viscosity tend to have be polar molecules and tend to be large molecules. And so, for instance, the main reason that syrup flows slowly is because it's a large molecule. Whereas the reason water flows easily is not so much because it's polar, that would indicate that it would have high viscosity, but because it's a very small molecule, so it flows fairly easy. So viscosity is a tough one to tell totally, but we can make kind of educated guesses. We can also take a look at surface tension. That's a direct result of the intermolecular forces. If we take a look at surface tension, basically it's the resistance of a liquid to spreading. So resistance of a liquid to increasing its surface area, or basically to spreading out. So the idea is, again, if I have high or strong intermolecular forces, then I'm going to have a high surface tension. An example of this is, of course, if we take a look at water and you look at, those little floaty bugs. What do they call those? We'll just put the floaty bugs, meaning that the water is more attracted to itself therefore has a high surface tension. And then, of course, if I have low or weak intermolecular forces, then I tend to have a small or low surface tension. And so what we're really saying is that if I take a droplet of water, the H2O is being attracted to itself, and so it wants to remain in that droplet. This also explains our concept of a meniscus. For instance, if I take a look at a narrow tube, we know that water forms a curved meniscus like this. And what this is basically the result of is two different forces. We've got the cohesion. That means the water is attracted to the water, and that's strong. And then we have what's called adhesion. That would be the attractive force between the water and, for instance, the glass. And that's very weak. And so water would much rather be attracted to the water than it would be to the glass. And if we compare that to a mercury one, and I have to admit this is awful hard to see because all of our examples of mercury are little thermometers, so they're very small, but they actually have an inverse one. And so here the mercury is attracted to itself more than the glass. Here the H2O is attracted to the glass more than the water. So depending upon the attractive forces holding things together and the attractive forces between, say, the water and the glass or the mercury and the glass, you're going to get different behaviors. So both properties, meaning viscosity and surface tension, are of course, related to the intermolecular forces that we've been talking about. And what that means is that they're both temperature dependent. Meaning, as we increase the temperature, we increase the kinetic energy available. Therefore, that counteracts it doesn't look like it's spelled right. Anyway, the intermolecular forces. Or if we think about it, we can kind of have three ranges of temperature. We can have where the temperature is much less than the intermolecular forces between the molecules, and that generally results in a solid phase. If the temperature is on the order of the intermolecular forces, that means we sort of have a liquid phase. And if I increase the temperature further, if the temperature is much, much greater than the intermolecular forces between the molecules, then we have a gas phase. So here, the temperature is too low to break the intermolecular forces. And so we have a rigid solution. Here, the temperature is not strong enough to break, but they are kind of what we would maybe consider flexible, or it allows them to kind of flow. And here the temperature is so high that the intermolecular forces are irrelevant or too weak. And so remember, in a gas, we've got those molecules zinging all along. Well, compared to the intermolecular forces that would attract those two molecules together, we've got so much energy in the kinetic energy portion of it that it can't actually, that those molecules don't interact. We're going to go into this in a lot more detail in Chapter 9. That's one of the things where if we do it out of order, it actually kind of benefits Chapter 9 in that we kind of know it ahead of time already. Okay, we also want to take a look at phase changes and intermolecular forces. And I have to be honest, this is mostly a review of Chapter 8 because I moved a lot of that material from Chapter 10 into Chapter 8. So there is a short worksheet on it, mostly to keep you honest and to remind you of the stuff from Chapter 8 that might show up on that test in Chapter 9. So that's that diagram where we kind of looked at it like this, where we put temperature and then we added heat. And we had a curve that looked like this, where here's our 0 degrees Celsius, here's 100 degrees Celsius. And so this is, of course, our curve for water. All other substances are going to have similar curves. The only thing that's going to differ is the numbers on the y-axis and then the amount of energy that would have to be added on the x-axis. And then we said that this was our solid. This is solid plus liquid. This is our liquid portion of the graph. This is our liquid plus gas. And that's our gas portion of the graph. And notice that in chapter that we had equations to describe these. This is Q equals ms delta T, where remember that we just looked that up in a book. It's just our constant. And then and that applies for any of the curved parts of the graph, meaning we're in pure phases. And then we had for the flat parts of the graph, and I guess I'll do that in a different color, just sort of remind people. So the flat portions, that's where our phase changes occur. And our formula there was that the amount of heat necessary to do that is equal to the mass times our delta H value. And we called this vaporization. And this is delta H of fusion. So you use a different delta H per thing. And so the idea is that between those two equations, Q equals ms delta T and Q equals m delta H, we really could go and fill in all of the amounts of energy on here. And so one of the things that you're going to have to do on your homework is you're going to have to break it into 5 steps, and you're going to have to go step 1, 2, 3, 4, and 5, and figure out how much energy it takes to do each of those parts. And so basically this is essentially figure 10.10 on page 367. Now, if you're using a different version of the book than the 5th edition, I don't know what page it's on, but it should be kind of in the same section if nothing else. So it really should probably be, figure 10.10 plus or minus 1 in your thing. And so what you can do is you can use each of those equations to solve for those. So an example would be if we know, or we wanted to calculate the energy required to heat an ice cube from minus 10 degrees Celsius all the way up to 100 degrees Celsius. And we know from looking in the book that it's 2.03 joules per gram degree Celsius is what the S value is, or the specific heat for water solid, and the specific heat for water liquid is 4.184 joules per gram degree Celsius. So this is S from the book. And then we also know that we can look up delta H of fusion from the book for water. That's 6.01 kilojoules per mole. And for instance, delta H of vaporization is 40.67 kilojoules per mole. So notice that when we're kind of doing this problem, we've got grams for some parts and moles for others. And so, we're constantly going to be converting between grams and moles, but that's just our molecular weight. And we know the molecular weight of water is 18.01 grams per mole. So we can kind of do those calculations as many times as we want. So for example, if I wanted to have the energy required to heat an ice cube from minus 10 to 100 degrees Celsius, well, if I kind of sketch out that graph again, since I used too many colors on the last one, notice that, here's 0 degrees Celsius, here's 100 degrees Celsius, and so if I pretend to start off at minus 10, then I've got 4 parts to that problem. I have to first calculate that step, then I have to calculate the amount of energy to go from a solid to a liquid, and then I'm simply heating the liquid, so I'm increasing the temperature, so that's step 3, and then step 4, I'm again going from a liquid to a gas, because I want to heat the ice cube from minus 10 degrees Celsius to 100 degrees Celsius, and I want that to be a gas. And so I've really got 4 steps that I'm doing in that process. So step 1 is simply going to be going from a solid at minus 10 degrees Celsius to a solid at 0 degrees Celsius. That's just Q equals ms delta T. And I forgot to add, and I always forget to do that, assume a 100 gram sample, just because that's a nice easy number to use. So if I do Q equals 100 grams times S, which is 2.03 joules per gram degree Celsius, times my change in temperature, which is 10 degrees Celsius, I can get that value. Step 2 is, from that chart, is going from a solid at 0 degrees Celsius to a liquid at 0 degrees Celsius. So that's our phase change. So remember, if I'm increasing the temperature, that's just increasing kinetic energy. And if I'm doing a phase change, all that energy is going to overcome the intermolecular forces holding the molecules together. So here I use Q equals m delta H. So in this case, I take my 100 grams of H2O. I know there's 18.01 grams per mole. And then I know that that value from the previous page is 6.01 kilojoules per mole. And to keep my units constant, I should say that 1 kilojoule is 1,000 joules, and I get that answer in joules. And so I can keep doing that process for the other 2 parts of the graph, and then of course I can simply add up the total amount of energy. So add steps 1 through 4 to get the final answer. And I know I kind of went through that fast, and that's really because this is a review of what we covered in Chapter 8. And so I didn't want to kind of do it too much. The other part that we want to pull from Chapter 8 is the concept of delta G equals delta H minus T delta S. And remember that this temperature represents the equilibrium temperature, where delta G is equal to 0 for phase changes. So for instance, if we have a table where we know that delta H equals 6.01 kilojoules per mole for delta H of fusion, and I know that my delta S of fusion is equal to 22 joules per mole K, then I know that when delta G equals 0, that's the transition from solid to liquid. And so if I solve this equation, I can rearrange it to get T equals delta H over delta S. And so I know that if I plug that in, temperature equals 6.01 kilojoules per mole, and delta S is 22 joules per mole K. Notice my moles cancel out. Because delta S is usually measured in joules and delta H is usually measured in kilojoules per mole, we got to do one quick conversion. 1,000 joules is 1 kilojoule, and then my kilojoules and my joules cancel out, and I can calculate that temperature, and I get, for instance, in this case, 273 Kelvin, which is 0 degrees Celsius, which, remember, we know that the melting point / freezing point of water, or that transition from solid to liquid, really does occur at 0 degrees Celsius. So given these values, we can calculate that temperature for any given phase transition. So all we have to do is have a giant table of delta H and delta S values, like for instance Appendix B or C in your book, and we can calculate the temperature for any given phase change that we want. And then maybe the last bit of review is kind of thinking about it in terms of energy, is if we have a gas up at top and we know liquid is in between and solid is down here, we know that we can take these phase transitions and we can keep track of the delta H values. For instance, if I go from a liquid to a gas, that is vaporization. And we know that delta H is greater than 0, delta S is greater than 0, because it requires energy in order to convert it. So it takes energy. And so it's non-spontaneous here, but it's spontaneous due to entropy, meaning we go from a ordered system, kind of the liquid, to a disordered system, the gas. And so if we know those delta H and those delta S values, we can figure out what temperature that occurs at by just taking the ratio, oops, not delta V, delta S, the ratio of them to figure out what they are. Let's see. Okay, so that's kind of the properties of liquids. The next thing we want to kind of look at is that transition from a liquid to a gas in more detail. And what we have to remember here is that this is a sort of an equilibrium. And so remember, that was what we called evaporation. And that's the process of going from a liquid to a gas. And we can explain this using the kinetic molecular theory of gases. But that's from chapter 9, and so we're going to kind of delay that. And instead we're simply going to kind of take a look at a general idea where we know that if I have a liquid and that if I have gas molecules, that I constantly am going from liquid to gas, and at the same time those gas molecules are being continually going from the gas state to the liquid state. And so what I really have is an equilibrium between the liquid and the gas. And what we can recognize is that we have to simply break the intermolecular forces holding the liquid together. To form a gas. And so we won't worry about sort of that whole kinetic molecular theory and talking about the fact that the molecules are in constant motion. Instead, we can kind of think about it from simply breaking those intermolecular forces. And we know that if the energy available is less than the intermolecular forces, or on the order of the intermolecular forces, I should say, then we kind of have a liquid state, whereas in the gas state, our energy has to be much, much greater than those intermolecular forces present. So, what are some properties of evaporation? Well, first off, we know that in a closed container, that evaporation is independent of the size of the container. Doesn't matter if you have a big or a small container. We know that the evaporation is also independent of the amount of liquid. Meaning the rate at which something evaporates doesn't matter if I have a little body of water or a giant body of water. The evaporation rate should be the same. And we know that it's dependent on the intermolecular forces involved. And so if we have strong intermolecular forces, then we're going to have low evaporation, meaning it takes more energy to evaporate it. And if I have weak intermolecular forces, then I'm going to have a high rate of evaporation. So it's independent of the size and the amount, but it is dependent on the intermolecular forces. And that also means, since intermolecular forces are dependent on temperature, it's also dependent on temperature, meaning high temperature equals lots of evaporating, and low temperatures means very little evaporates. Another way we can kind of think about it is if we draw this graph, and I like this graph. It actually shows up in Chapter 9 also, but since we're doing it out of order, this will be your first time of seeing it. So if this is the number of molecules, then this is the kinetic energy of those molecules. What happens is if I have a low temperature, that means I have a lot of molecules with very little kinetic energy, and then that graph dies off like that. So that's low temperatures, meaning low kinetic energy on average. And then if I take a look at the high temperatures, what that does is that decreases the amount I have at low temperatures, but it increases the overall amount I have at higher kinetic energies. And so this would be high temperature, meaning I have an average higher kinetic energy. And then if I simply pick an arbitrary point on this graph, for instance, for water, that arbitrary point might be 100 degrees Celsius. Then what we notice is that at higher temperatures, there's a larger number of molecules with energy high enough to go from the solid to the liquid state. Whereas if I take a look at low temperatures, then that's just the blue part, there's a lower number of particles with enough kinetic energy to go from, sorry, not solid to liquid, I meant liquid to gas, since that's what we're talking about, evaporation, from liquid to gas here also. So that basically at any given temperature, some particles have that ability to evaporate. Some particles have the energy required to go from a liquid phase to a gas phase, meaning to break the intermolecular forces, but that at high temperatures there's more particles. So the higher the temperature, the more atoms there are that can go from the liquid phase to the gas phase, and so we have more and more atoms doing that. We can define the vapor pressure as simply the pressure of a gas above a liquid at equilibrium. And what it really is for our intents and purposes is it's the number of molecules in the gas phase over the number of molecules in the liquid phase. And so, for instance, at low temperatures, very few molecules have enough kinetic energy to go from a liquid to a gas, but at high temperatures, we can have lots of molecules that have enough kinetic energy to go from the liquid to a gas. So as a general rule, the vapor pressure is proportional to temperature, meaning as the vapor pressure increases, as the temperature increases, the vapor pressure increases. But the vapor pressure is inversely proportional to the intermolecular forces, meaning if I have strong intermolecular forces, I have a low vapor pressure. That means there's few molecules in the gas. And if I have weak intermolecular forces, then that means that I have a high vapor pressure, and that means there's lots of molecules in the gas phase. And so if we take a look at it, the vapor pressure basically gives us insight into the intermolecular forces, or they sort of correlate, or if we make observations about something's vapor pressure, then we can know something about the intermolecular forces holding those compounds together. Or vice versa, if we know something about the intermolecular forces, we can make a statement about the vapor pressure. We can also talk about the boiling point real quick. That's when the vapor pressure is equal to the atmospheric pressure. So if we expand our picture just a little bit, what we have to realize is that we've got the pressure of the atmosphere pushing down. And so in order for something to boil, those gas molecules have to overcome that atmospheric pressure. And so the definition of the boiling point is simply when they're equal. And what that means is that because the boiling point is defined as when the vapor pressure is equal to the atmospheric pressure, boiling point is inversely proportional to is directly proportional to the intermolecular forces. And it's inversely proportional to the vapor pressure. Meaning something with a high boiling point has strong intermolecular forces, but it means it has weak or low vapor pressure. So if you can kind of remember this little statement about what's proportional to what, and remember that vapor pressure is basically inversely proportional to the other two, then again you can make insights into things. For example, if we take a look, and there's a picture in your book, it's figure 10.13, and that's on page 370. But since I know a lot of people never bring their books, we'll just sketch it out real quick. If we take a look at vapor pressure, in millimeters of mercury. And I should probably go back because I forgot we're doing this out of order. Let me go back real quick and talk about, just a second, the units for pressure. And this is one of those things where I forget that people don't know this always. Essentially, remember what pressure is its force over area. And so if we kind of think about a balloon, it's the force of the gas that's trapped in that balloon pushing outward. And the typical units for pressure are kind of various, meaning millimeters of mercury is probably the most common one. Sometimes that's called torr because it's named after this guy named Torricelli that first invented it. And that comes from the fact that if I take mercury, so I've got a pool of mercury, and I invert, say, a test tube in it, then the atmospheric pressure pushing down will cause that mercury to rise up in that tube a certain distance. And that's where we get that unit of millimeters mercury. And because Torricelli is the guy that came up with it, sometimes the unit is named after him in terms of torr. And this is, of course, a vacuum. And so you can think about this as basically we know about barometers and stuff like that. We'll go into this a lot more detail in Chapter 9. For now, we just need to have the units there for us available. The other thing you sometimes hear it measured in is terms of atmospheres, pascals, or for instance even PSI, which is just pounds per square inch, pounds per. And that essentially at sea level, to give you guys kind of an idea, it's about 760 millimeters of mercury. And if we're up here at Rangeley, which is about 1 mile high, we're on the order of, and of course I don't have the number sitting in front of me because that would be silly to follow along in my notes that much, about probably 720 millimeters of mercury or something. Meaning, because we're a mile high, we have less atmosphere pushing down on us. So the key here is to recognize that our normal measuring point is 760 millimeters of mercury, which is equal to 1 atmosphere. So if we take a look at this graph, the key point for us to realize is that we want to have and know where 760 millimeters of mercury is on that chart. And we don't really care where the rest of the chart is. And so if we take a look at that chart, we can plot it for 3 compounds. We've got ether, which if I take a look at its Lewis structure looks like this. And so notice that this really only has London dispersion forces and very weak dipole-dipole due to that oxygen bond. I can compare that to, for instance, ethanol, which has a similar formula to it, but instead of having that oxygen in between the carbons, we have an OH group. That means is that I have London dispersion forces, LDF, and of course I have very strong dipole-dipole, and we actually call that a hydrogen bond due to that OH group. And then the last compound we can talk about is water, and we know that that looks like this. And that has, of course, London dispersion forces, but it also has strong ×2 hydrogen bonds, meaning it can make a hydrogen bond with both of those. And so notice that if I'm kind of, labeling them, this is low intermolecular forces, and this is something that has high intermolecular forces. And so notice that at any given temperature, for instance here, if I draw a line down, this corresponds to, well, I'm going to do this in Celsius, screw that, 100 degrees Celsius for the boiling point of water. Notice that this point is where the vapor pressure is equal to the atmospheric pressure. And then for ethanol, that value is smaller. It's on the order of, I want to say, 83 degrees Celsius. And then for ether, that value is at an even lower temperature. It's on the order of, let's see, about 30 degrees Celsius. And so notice that low intermolecular forces equal a low boiling point, but that if I take a look at the value of the vapor pressure at any given temperature, it has a high vapor pressure, whereas at any given temperature for water, it has a low vapor pressure. So the idea is that if we measure the vapor pressure curve of something, or even if we simply just measure the boiling point of something, it tells us something about the intermolecular forces responsible for holding those atoms together. Now, notice that these produce curved graphs when we plot them. One of the things that chemists love to do is we need to figure out how to make a linear graph, because curved graphs suck. Linear graphs are much easier to do. And so we have what's called the Clapeyron equation. And what that simply says is that the natural log of the vapor pressure is equal to minus delta H of vaporization all over R times 1 over the temperature plus a constant. And so this is just pressure, usually in millimeters of mercury. This is delta H of vaporization, which is in terms of kilojoules per mole. R is something we call the gas constant. It has a value of 8.314 joules per K mole. Temperature for this has to be measured in Kelvin, and then C is simply a constant that's different for every gas. And you'll notice that if I look at that, that looks a lot like y equals mx plus b, where y is simply my vapor pressure. M is the slope of this line, so that means m is minus delta H of vaporization over R. X means that we plot it versus 1 over temperature, and then again, we don't worry about that constant term so much. So what that means is that to make a straight graph, if I plot the natural log of the vapor pressure versus the temperature 1 over the temperature in Kelvin, then I get a straight line whose slope is equal to minus delta H of vaporization over that gas constant R. And of course, I guess, like I said, we don't really worry about it, but that's the y-intercept. And so one of the things that we can do is simply by measuring the vapor pressure at a given series of given temperatures, we can actually calculate that delta H of vaporization transition. So for instance, if we do a graph, and which slide shows it in? Oh, here it is. It's at the beginning of this slideshow. What I did is I took a bunch of data for water, and this data is in your book. You can reproduce the graph if you really want. Or given data from another graph, you should be able to reproduce it. But notice that I've got the data in a series of formats. This is degrees Celsius versus the vapor pressure. Then I also did it in Kelvin versus the pressure. And then there's that 1 over temperature, and then there's my natural log of my pressure. And so if I take a look at it, I get my normal evaporation curve. So that's, if we connect all the dots together, notice that at 100 degrees Celsius up here, or essentially 373 Kelvin, that vapor pressure is equal to the atmospheric pressure. And, if I had wanted to, and not to overload the graph, but remember that we can also say that there was our ether line, and we can kind of sketch one in, and that would have ended up being our ethanol line. And then if I instead plot natural log versus 1 over T, then I get a nice straight line, which simply says delta H of vaporization equals 5, oh, that's equal to, delta H of vaporization is equal to R is equal to 5202.6. And we can multiply by R to get the real delta H of vaporization value. And so take that times 8.314 and times 1,000, and you should get approximately 40 kilojoules per mole, which, you know, matches up nicely with the value in the book. I guess I should have included that calculation. So the idea is that we can just simply measure the data, or we can actually, if we know the equation, if we know delta H from some other measurement, we can actually draw that entire graph out using the Clausius-Clapeyron equation. And then the second form of the Clausius-Clapeyron equation, probably the more useful form, is relates 2 points. Which is natural log of P1 over P2 equals delta H of vaporization over R, T1 minus T2 all over T1 times T2. I'm not going to bother deriving that, but that's basically relates any 2 points, temperature, pressure points. And so what that means we can do is we can ask little questions like, for instance, you know, I know that at 100 degrees Celsius, the vapor pressure is equal to 760 millimeters of mercury for water. What is the vapor pressure at 50 degrees Celsius? So we just have to go in and realize that if I look at it, I've got P1 equals 760, T1 equals 100 degrees Celsius, P2 is what we're solving for, and T2 is 50 degrees Celsius. And so if I take it, the natural log of 760 all over P2 is equal to delta H, which is 40.8 times kilojoules per mole, times R, which is 8.314, I'm sorry, divided by it, for joules per mole Kelvin. Again, for whatever reason, we have to, well, I shouldn't say whatever reason, but some values are given in kilojoules, some values are given in joules, so I need to make sure I kind of cancel all those units out. Notice my moles cancel. And then for the temperature part, you know, a bar problem doesn't really allow you to do subtractions, so I kind of throw that in like that. And then 373 times 323. Notice that those temperatures have been converted to Kelvin. 100 degrees Celsius is 373 Kelvin. 50 degrees Celsius is 323 Kelvin. I get 760 millimeters of mercury all over P2 equals 2.036, oops, natural log. And then the way we get rid of natural logs, and I'll continue this on the next page, is we simply take and do the opposite of a natural log, which is e to the 2.036. Then, of course, I can solve and rearrange for P2. It's just 760 all over e to the 2.036. And so P2 equals about 99 millimeters of mercury. Now, notice that that's not the exponent key. It's actually the anti-log key. And I got to be honest, I don't know on your super fancy calculators what that's going to be labeled as. If you want, what we can do is bring it up after class and we'll take a look at it. Otherwise, we'll just kind of make that assumption that, you can figure it out on your calculator. Okay, so what we're going to say is that homework 10, 10A was due Tuesday. 10B and C will be due Wednesday. And then we'll pick up in chapter 10, starting in 10.6 with different types of solids. So the first three, 10A was basically all about intermolecular forces. This is sort of about that liquid-gas transition and phase changes. And then what we'll do for tomorrow is we'll lecture for a little bit of time and then use the rest of the time for talking about or answering questions on